Hey everyone, I'm Corey Alexander and I go by flavors of Corey JA on the internet. This is a talk that I gave at RustConf 2023 and I wanted to record and get onto YouTube. And the talk is titled Using Rust and Battlesnake to Never Stop Learning. So let's dive in. What is Battlesnake? We're going to need a bit of background to get started. I thought it would be good to start by watching a game. My snake here is hovering Hobbs, and they're competing against Fang Fiend by Justin13888. Hobbs is the orange snake with a puffin head and wearing jorts as a tail. In Battlesnake, you unlock new heads and tails to use, and Hobbs won these, being the People's Choice winner in a past tournament. So Hobbs and Fang are going to run around this board, trying to eat the food to grow longer and avoid running into another snake or the edge of the board. Our goal is to be the last snake alive on the board. We're going to try to outmaneuver and trap the other snake. I picked this game myself, so of course we'll watch Hobbs take the win here. Sorry about that, Fang Fiend. So Battlesnake is a coding game. You're building the brain to one of these snakes, and you compete against developers from all over the world trying to build a snake that can survive the longest on the board. I'm going to give a quick rundown of the basic rules of Battlesnake. It's okay if you miss some of these. It's not super important to the talk, but helps to explain the game. In Battlesnake, the goal is to be the last snake alive on the board. Each turn, you decide which direction your snake is going to go. Up, down, left, or right. Each snake has a health that starts at 100 and goes down by 1 each turn. If it reaches 0, the snake is eliminated. Eating the red food pellets increases your health to 100 and increases the length of your snake by 1. If 2 snake heads land on the same square at the same time, the longer one wins and the smaller one is eliminated. If the snakes are the same length, they're both eliminated. On each turn, the game engine sends a request to all the competitors with the full details of the board, where all the snakes are, their healths, and where any food might be. Each snake has 500 milliseconds to return a response to that request with their move: up, down, left, or right. The most important thing to take away from this is that 500 milliseconds. Each turn, you only have 500 milliseconds to decide which direction to go. That means that every moment is vital. Today's talk is going to follow my journey through building my first few snakes and some of the learnings along the way. I'm a Ruby web developer by trade, an avid Battlesnake player, and I've been using Rust to build my snakes and learn about memory representations, benchmarks, flame graphs, and more along the way. We'll see how Rust and Battlesnake helped me keep learning and growing as a developer while also having fun. So I'm a Ruby developer by day, so why did I choose Rust? Mostly because I enjoyed it, and I still do. And a bit because I knew Rust was going to be faster than Ruby, and in Battlesnake, speed matters. I also wanted to use Battlesnake to keep learning and growing as a developer. Since I use Ruby day to day, I wanted to try something different. Since Battlesnake is a competitive game, it kept me coming back, learning new tricks, and learning more about Rust along the way. My first snake was a simple snake. It looked just at the current board to decide where to move. Maybe there was food to the left, so going that way made sense. Or maybe there was a smaller snake to my right that I could try and corner. Quickly though, I wanted something more complex. Simulating moves. Now instead of just looking at the current board, I wanted to look into the future and make simulations. I wanted to look at every possible move for my snake, and from each of those, every possible move my opponents could make. By doing this, my snake could see all the possible futures that could be. This strategy of creating a tree of possible games is generally called tree searching. The start of any good tree search algorithm is building up the tree of possible moves and game states. We start with our current game state as the root node of our eventual tree. Then we start simulating moves in the future. First, we look at all the possible moves our snake could make. We could go up, so we make a copy of the game state and move our snake up one. Or we could go right, so we make a new copy and move our snake to the right. Or finally down, where we make one more copy and move our snake down. You can see how the head moves to a different square in each of these new boards. My snake is moving as we simulate moves. Now we can repeat this process for our opponent's moves this turn. For each of these new nodes, we branch again for each move my opponent could make. We'll do these ones in bundles. When I go up, my opponent could go in any direction, so we create branches for each of them. We do the same for the right subtree. And finally on our down subtree. You can see how quickly this tree gets really big. It grows exponentially. After just one turn and 2 depths in our tree, we are already at 9 nodes. And going 2 turns, or to a depth of 4, is 81 nodes. So for each turn, the number of nodes increases by 9. Most of my snakes use Minimax, which is a tree search algorithm. We aren't going to talk about the details of it too much, but it works by scoring the bottom leaf nodes and using the scores to determine which of my possible moves is best. So the further down our tree we can look, the better a decision my snake can make. When I finally got my tree search working for the first time, my snake could simulate about 4 turns into the future. So for a standard duels game of Battlesnake, where we have two snakes, we're looking at something like 6,500 game states that we can look at in 500 milliseconds. And we'll see how different Rust learnings help me boost my speed and my fortune-telling abilities. With our Battlesnake intro out of the way, it's time to get back to Rust and talk about our first learning. When I got started with my snakes, I wasn't doing anything to measure performance. So every time I tried something to make my snake faster, I'd have to deploy my snake and wait for games to run overnight. Then I could finally look at the results in my logs and see how I did. But this was a really long feedback loop. Every change I wanted to test meant I needed to wait overnight for enough games to run. I wanted a better way to measure performance of my snakes. And thanks to Rust and Cargo, it was easy to know where to start. When I started playing Battlesnake, I hadn't written benchmarks before, but I knew I needed to start measuring my performance if I wanted to improve it. It was awesome to learn that benchmarks were built right into Cargo, and even better, they were just as easy as tests. All you have to do is add the bench attribute above a function, and then you call it with cargo bench, and that's really all there is to it. Cargo goes ahead and runs our little function a couple of times and reports the average for us. So Rust taught me that benchmarks could be easy and live right in the code base with everything else. I was measuring my code and able to see what changes made things faster and what made things slower. This got me a bit more scientific. Now instead of making random changes and hoping for the best, I could measure the performance of my code and know for sure when I made things faster. And with that, we've learned a bit about our first topic, benchmarks. Rust helped me learn that benchmarks didn't have to be complicated. I poked around a bit randomly and tried some things out. Some small gains here, a failed experiment there. But finally, things added up and I was seeing some pretty big improvements. We could now look at about 20,000 board states in 500 milliseconds, which means we could see about 4.5 turns into the future. But to squeeze out even more performance, we're going to need to be a bit more focused. With benchmarks, we at least knew when we've made things better or worse, but it didn't really give us a place to look for possible improvements. But luckily I found something that could shine a light on code to look at for us, and that's flame graphs. Here's a simplified example of flame graph. Flame graphs helped show me where my snakes were spending their time. They work by taking stack traces while your program runs and graphing how many times different functions are called. Each block represents a function. Starting at the bottom, you can see the setup functions for our benchmark. These functions call our actual snake logic, which you can see is a layer above our setup code. The higher up our blocks go, the higher up the call stack we are. And the more horizontal space a block takes, the more time our program spent in that function. And with our new flame graph knowledge, I was able to find some low-hanging fruit and make my snakes a bit faster. My benchmarks were now able to look at just over 60,000 board states, or 5 turns into the future. In a flame graph, taking up a lot of horizontal space doesn't necessarily mean that something's slow though. It could be a relatively quick function, but it's simply called a lot. It's something you do a ton of times, even though each time you call it, it's fast. And that's what I ended up with after a few iterations with the flame graphs. I found a function that I hadn't really considered before. It was always fast to call once, but it turns out I was calling it a ton of times. And that function was clone. Clone was being called a lot, and my snakes were spending a significant portion of their time making copies of various structs. This surprised me. I came from Ruby, so thinking about memory this deeply was new to me. See, when I got started with my snakes, I didn't understand lifetimes or references. And when I got my first implementation working nicely, it was simply by cloning everywhere. I didn't think about lifetimes, and every function I wrote took ownership of its arguments. So each time I called a function, I needed a copy of my structs, I simply cloned them. And the biggest offense was in my tree search code, which we looked at before. Starting from our root, each time we needed to make a branch, we made a new copy of our original game board, and then we'd move our snake. And I didn't really think about what was happening under the hood. I just saw each clone as a way to make the compiler happy. But eventually, Rust taught me to see it for the benefit it really was. Each clone call was work. We needed to allocate memory and then copy over all the data from our original structures. And I could work on hunting down and removing all the clone calls from my tree search to speed things up. We're gonna go clone hunting now. So we have a new goal. Instead of our tree search making a clone for each node in the tree, what if we have a single board that we pass around? We start the same with our original board at the root, but now we move down the tree and we take our existing board with us and modify it. And if we do this in just the right order, we can walk this single board through the entire tree. We can first make this first move and explore this new node of the tree. Then we can reverse that move and get back to our original board state. And we can repeat this for all the other moves we're simulating. And the cool part is that even though we're only looking at a small tree with 2 layers, we can do the same pattern for any size tree and only keep this one board instance. And this removed a ton of my clone calls. Now instead of making a copy of our board state for each branch, we could keep a single board state throughout the entire tree. But for this to work, we do need something new. Before, we knew how to take a board and a potential move and evaluate that move on the board and move a snake. But now we need to be able to do the reverse. We need to be able to take a move and a board and undo the move. With these two new functions, we can walk through the entire tree without ever cloning our board. So no more clones! Woohoo! Our clone war was over. And through hunting down and clearing out all the clones, I began to understand data ownership and when it made sense to take something by reference versus by moving it. The Rust compiler was there to show me who owned the data and how it was moving between functions. The Rust compiler was there every step of the way, making sure I obeyed the borrowing rules. This was a great learning tool. I could trust that the compiler would catch any mistakes I made and keep me safe. And with all the clones and needless memory allocations removed, we were getting a lot faster. My snake could now look about 6 turns into the future. So we're now looking at something like 500,000 boards in half a second. That means we can look at about 1,000 board states in a millisecond. One of the great things about Battlesnake though is that it's a competitive game and always gives me a reason to keep improving. There's always more games to win and new opponents to beat. So let's keep going and check our flame graphs again. And there's 2 functions that are taking over our flame graphs. We're back to move and reverse move that we just talked about. It was faster than cloning the board, but it still took a significant amount of time to simulate moves and then reverse them. I was still spending about 80% of my time making moves and then reversing them in my snakes. And here is where I got a little stumped. Our flame graphs were pointing us to these functions, but I didn't really have any idea on how I was going to make them faster. But that's when something awesome happened. A gift was dropped on my lap. A solution to most of these problems appeared in the form of a new Rust crate specifically crafted for Battlesnake. And somehow, even better, it was made at least partially on livestream by fellow Battlesnake community member Fable and our own Sage from the Rust Foundation. And Battlesnake Game Types was born. Battlesnake Game Types was built from the ground up to be fast. It optimized both for a small memory footprint and to make simulating moves fast. And that simulating bit is exactly what we're looking for. But to see why, we need to look at our current board representation and take a look at simulating moves with it. This is the struct that holds our game state. We store the width and the height of the board. This tells us how big the board is for our snakes to move around on. We have a vec that contains the positions of all the food on the board. And finally, we have a vec of all the snakes. And the snake structs look something like this. Each snake has a vec that contains its body positions, starting from the head. So the first element in that vector is the head of the snake, and the last one is the tail. And each snake also holds onto its health. And finally, we have the position struct. This holds the x and y coordinate of the particular position. We use this to represent sections of a snake and to represent pieces of food in our food vec. And so now that we've seen how we store our board, we can look at what it takes to simulate a move. We start with this board on the left and want to have the purple snake go up. So looking at the body vec of this purple snake, we have these 4 positions, starting from the head and working our way down to the tail. So first, we have to shuffle down all the current body positions and remove the tail as we do. This moves the tail of our snake and makes room for our new head. Now we can insert our new head at position 0. And now our snake is the same length, but its head and tail have moved. This works, but it's not fast. Each time we move a snake, we have to reorder the whole vec. This adds up when we're simulating 5,000 moves in half a second. Battlesnake Game Types does it differently. We have a cell board struct that represents our entire board. This holds an array of cells equal to the size of the board. So in a 7x7 board, we're looking at 49 cells. I've labeled all the cells here by their index in the array. And each cell is this struct. We store an index representing which, if any, snake holds this square. And then we have the secret sauce here, the next index. And this is used to point to the next snake body piece. It works kind of like this. For a cell that holds the head of a snake, we point to the tail of that snake. And for a cell that holds any other snake piece, we point to the next segment towards the head. With this structure, if all we know is the head of our snakes, we can find all the other body pieces by following these pointers. First, we can hop from the head to the tail, and then we can follow the pointers until we reach the head again. Let's look at what happens when we simulate a move with this new representation. Here's our original board. I've drawn the next index as pointers instead of indexes to make it easier to see. First, we can find the cell that corresponds to our new head location, and point its next index to the new tail of our snake. We need to update the next index of the old head to point to this new head as well. And then we can store the new head as the snake head in our struct. And that's all we needed to do to forward simulate a move. And this took way less operations than the vec reorderings I was doing before. Plugging this into my snake led to some even bigger improvements in speed. We were now getting up to 6.5 turns into the future. And 6.5 turns into the future is 1.5 million game states in 500 milliseconds. And there's one more optimization I want to talk about real quick. The Battlesnake game types crate is also optimized for size. The standard cell board we looked at holds our entire board state in a static 382 bytes, way smaller than my vec-based approach and way easier to clone. Instead of creating new vecs and adding all the original data, we can do a simple mem copy to clone our new board. And since reverse move was something that our flame graphs pointed us to before, I was interested in making it faster. And what better way to make it faster than just remove it? I experimented one day with going back to the clones. With this new compact representation, cloning was so much cheaper that it became faster to clone the boards than it was to reverse the moves I made. And with that, I was able to look 7 turns into the future. And in a duels game of Battlesnake, where we simulate 3 moves for each snake, that's 4.78 million game states in under 500 milliseconds. We were able to get almost 100,000 game states in a single millisecond. And so with all this work, where do we fall on the leaderboard? Pretty well, if I do say so myself. I'm currently sitting at 8th place overall on the leaderboards. There are some awesome competitors and developers in that leaderboard, so I'm really proud to have made it up there. And if you look at the language tags here, you can see that 4 of us in the top 10 are using Rust for our snakes, and I think that's pretty cool to see. And that's all the time I've got for today. This talk doesn't even scratch the surface of things Rust has let me explore and learn. I've been able to explore threads, async, locks, and atomics, all from the comfort and safety that the Rust compiler provides. Thanks again, and remember, never stop learning.